Alai is the most dangerous sport in the world, with a ball that moves at a top speed of 84 meters per second, which is 188 miles per hour. The game is commonly played in Mexico and the Philippines. The game is played with a curved racket, the Xterra, which is used to catch and launch the ball, the pelota, off of walls. The ball is made of metal wire wound together and covered in goat skin. This is just like racquetball, but a lot deadlier, as the ball has a great density and it's moving fast, so it has a great deal of momentum to pass on to the wall or other players.
The world record for highlight ball is 188 miles an hour. This is the most dangerous game in the world. Nobody is killed, but they certainly get hurt.
This more dangerous than bullfighting?
Oh, sure. Every play, every point is potential death.
I'm scared.
An orange is heavy, but it'll probably come out easily 100 miles an hour.
How accurate are they?
It might take about, I would say, 3 shots, 2 practice shots, and the third one I'll get him.
I'm not looking forward to this at all.
There you go. Let me see this one right here. Let's go.
This is the end.
When the rounded part of the Xterra ends, which direction does the pelota, the ball, go? Well, we're going to assume that it has a rounded shape, so when the path ends, it moves straight, tangent to the curve. So when the force that's being applied by this Xterra stops, the ball leaves the circular path, tangent to the curve, and moves straight. This is how highlight players learn to aim. Let's assume a scenario where we have a highlight ball, the pelota, which has a top velocity of 84 meters per second and a mass of 0.127 kilograms. The Xterra has a radius of 0.457 meters, about half a meter. We're going to find the acceleration first. The acceleration only utilizes part of these formulas. Remember, there's a formula for whether we have velocity for period, which is capital T, or the frequency, which is lowercase f. In this case, we're finding just the centripetal acceleration. We have the mass and we have the radius of the circular path. Every formula uses mass, every formula uses radius. So we're going to find the one that has velocity. But we're just finding acceleration, so mass is not included. If we were finding the force, mass would be included. This is part of Newton's second law. Force equals mass times acceleration. So I'm going to use just this portion of the formula. I'm going to plug things in. Replace my variables with parentheses so I have a place to plug a value in or substitute a value in. I'm going to plug in 84 for my velocity, and I'm going to plug in my radius. Whenever I have a formula that is a ratio like this, or a big fraction, I'm going to simplify the top, then simplify the bottom. So I'm going to do 84 squared before dividing by 0.457. I get a total of 15,439.82 meters per second squared. So a pretty high acceleration for this little ball. If we take the same exact scenario and we want to find the force, we're going to use the same set of formulas. In this case, we're finding the force, so we're looking at mass times velocity squared divided by radius. Write the formula out, substitute parentheses in, so I have a place to substitute my given values in. I have my mass, I have my velocity, and I have my radius. Simplify everything up top, simplify everything down below before dividing. Treat them as two sets of order of operations, as if they're in two sets of parentheses or grouping symbols. So I'm going to square 84. I'm going to multiply that by 0.127 and divide that whole product by 0.457 to get 1,960.86 newtons. This is how we use our centripetal force formulas in order to calculate different variables, including the acceleration and the force applied to keep the object moving in a centripetal or circular motion.